In this video, I'd like to guide you through some of the key aspects when designing this board you're seeing in front of you right now. This is a rather small board, even though it looks quite big on the screen, but it's an M.2 form factor, so common SSDs these days, which can fit into laptops, form factor with an FPGA, a fairly beefy Artix 7 by Xilinx, some DDR memory, some flash RAM, quad buck converter, and so on. The special thing about this board is, or the purpose of this board, is that this is a PCI Express FPGA hardware accelerator. So you can plug this module with this M.2 slot on the right side here into your laptop, into your computer, and offload, for example, some parallel processing tasks onto the FPGA. I'd like to guide you through how I came up with the DDR pinout, because FPGAs, of course, are very flexible, so the pinout isn't fixed for a particular memory device. And I'll show you how to do that in Xilinx Vivado. Also, I'd like to show you how I came up with this footprint and also the pinout of the M.2 connector, some PCI Express routing guidelines, and more. This board was manufactured and assembled by PCBWay in China, who are also very kindly sponsoring this video, and more about them later and the ordering process I went through and which files I had to supply to get this board manufactured and assembled. This PCB I designed using Altium Designer, which is my ECAD tool of choice for especially more advanced designs such as this, with many advanced features. If you'd like to give Altium Designer a try for yourself, make sure to go to altium.com/yt/philslab to get yourself a free trial of Altium Designer. I have various other videos on my channel describing and detailing Altium Design and how to use it, so make sure to check out those videos as well. Looking at the bottom side of the board, this is in total an 8-layer board, a lot of them of course dedicated to ground or power, and about 4 signal layers. On the bottom side, if we zoom in, we can see a lot of the DDR bus routing, which is time matched and impedance controlled, and I'll show you how to specify that when you order your boards as well, and a lot of very small passive components. So 0402s, for example, where my mouse cursor at the moment at the center of the screen, this is 0402, but the even smaller packages are 0201, so very, very small. The PCBWay has assembled them pretty much perfectly. We'll go through the capacitor, selections, power supply, and so forth in this video. When ordering with PCBWay, I typically, for more advanced PCBs such as this one, I use the Advanced PCB service, which is this 4th item, and these have far more options and more unique capabilities rather than the standard PCBs. So you can have even just a single PCB produced up to a mental 60 layers, various materials, thicknesses, minimum hole sizes, and so on. For this M.2 form factor, because it has to fit in a card edge slot, I had to go with 0.8 millimeters, and you can see for 8 layers, it happens to be that 0.8 is the minimum thickness they can produce. You also saw that we're using edge connector, so I had to enable the edge connector option, and we can even choose beveling, so angling off or chamfering the edge connector. You of course also need a different plating for the edge connector, because this will be pushed in, pushed out quite a lot. So if it's a very soft material, this will rub off or wear out pretty quickly. So we can use hard gold or different material for the edge connector. In the additional options further below, I also used a custom stack up, impedance control, and I used half cut or castellated holes. The castellated hole being on the left side over here. This is to fit a screw to attach, for example, to a laptop's motherboard. Looking at the price, of course, this is a fairly unique project. The PCB, of course, is fairly advanced. It's 8 layers, very thin at about 0.8 millimeters, impedance controlled, custom stack up, edge connectors, and so forth. So, of course, it's going to cost a bit more. In total, I had 5 pieces produced, 3 of them assembled. So for 5 pieces, it's about $120 per PCB, which I think is very reasonable for some advanced PCB like this. Then adding on top assembly for 3 pieces, $390, which includes component cost as well. So fairly reasonable for such an advanced PCB. This is a very short run through of some boards we'll be looking at in an advanced PCB design course I'm currently working on and hope to release at the start of 2023. This will not only cover the details of this particular board we're looking at this video, but other Xilinx FPGA and system-on-chip based boards, including how to root out DDR3, many different aspects such as choice of capacitors, looking at impedance profiles, power distribution networks, stack-ups, build-ups, and much, much more that'll explore this in much, much more detail. If you'd like to stay up to date to this course, I'll leave a link to this Google Forms where you can sign up with your email and be notified when this course is available. Here I now am in Altium Designer, just on the home page, and on the left side you can see the Atlas M.2 project. The PCB's name is Atlas, fairly random choice, but I've divided up into an overview schematic and various different schematic pages. Because FPGA schematics tend to grow rather large, I prefer having this split across multiple pages. But we'll go through them one by one and see what design decisions I made. Let's start off on the power page. Now, FPGAs typically require many different voltages, including core voltages, DDR voltages, and so forth. In this particular example, because I'm also using PCI Express, the Artix FPGA we're using required a 1.2 volts for the PCI Express transceivers, as we'll see in just a tiny bit. This particular IC is really nice because it has certain fixed output voltage configurations and maybe one adjustable voltage channel. If we go to the datasheet for this IC, I've happened to use this top row here, so the A version of this device. Each buck channel can deliver up to 1.5 amps, and all of the 4 output voltages are adjustable. However, in some designs, for example, if you are running a simpler FPGA, you might have a 3.3 volt bank voltage, you might have a 1.8 volt auxiliary voltage, 1.3 volts for DDR memory, 1.2 for another peripheral, for example, some transceivers. I went there with a completely adjustable version because I need 4 specific different voltages. My first voltage is 1.0 volts, and because of the reference voltage of the feedback node, I do not need a divider network here. So I get 1.0 volts here, which is for my core voltage. I have 1.2 volts, which are for my PCI Express transceivers, 1.8 volts for my auxiliary supplies, and 1.5 volts for my DDR3 memory. If we're using DDR3 low power memory, we might go with 1.3 volts instead. All these values, inductor values, capacitances, and so on, I simply just took from the datasheet. I always try to practice BOM consolidation as well, so bill of materials consolidation, so using many of the similar parts, so my bill of materials or the number of unique components on my bill of materials doesn't grow too large. So all of these are 1.5 microhenry inductors, all of my output capacitors are 47 microfarads, for example. With FPGAs, we also have to think about startup or power supply sequencing. We can't just turn on all of these output supplies at the same time or ones before others. And you can get this from, for example, the Artix datasheet, and the particular startup sequence we want is the input voltage, then 1 volt, 1.2 volts, 1.8 volts, and finally 1.5 volts. With these more advanced buck converters, you will typically have power good signals. So once the operating voltage of the output is within a certain range, maybe plus minus 5%, this power good signal, which is typically open drain, so we need a pull-up resistor, will go high. We can then use this power good signal going high, to trigger the enable signal of the next buck converter stage, and this is how we can then do startup sequencing. It can oftentimes also be helpful to place a small capacitor on the enable signal, and that in combination with a series resistor will form some sort of low-pass filter, essentially a small time delay. Other than that, I simply have some input capacitance as recommended per the datasheet, and that's about it. Jumping over briefly to the PCB design, here in Altium Designer I have my buck converter laid out. It's a fairly small QFN package, and it's nicely symmetrical, so I can place all of my components nicely arranged along the X and Y axes. That makes it look fairly symmetrical, and that I have small loop areas. Going to 2D view, I might have my switch node output, which I want to keep fairly small and short because it's a high frequency, typically high current switch node feeding into my inductor over here. Output for my inductor goes into my output capacitor, and the ground node of my capacitor tied to vias to my internal ground planes. Again, trying to keep my loops as small as possible, and the same goes for the other 3 channels. Feedback resistor wise, I've put them on the other side of the board. All my feedback networks, we can see this better in 3D view if I turn around, all of my feedback networks on the bottom side away from the inductors, trying to maintain as much physical space and separation, and of course the internal ground planes help as well. So try to keep your loops nice and small, nice and tight. Try to keep feedback elements away from magnetic elements such as inductors. In terms of power distribution, in this 8-layer board I have my top signal layer, bottom signal layer, various internal ground planes, internal signal layers, but also an internal power layer. So from my buck converter, I have various polygon pores feeding my FPGA or wherever these voltage rails need to get to. And typically this is a good idea, especially for higher frequency designs, because we get nice low inductance from these power and ground plane pairs, as well as wide enough paths so we get all this current through this board. Also great for thermals as well, of course. The input power is coming from this M.2 edge connector, which is nominally at 3.3 volts. Next, let's move over to the various FPGA sections. Now, FPGA footprints are typically BGAs with fairly not large ball counts. The particular FPGA I'm using is the Xilinx 7 Series Artix 35T 484 ball BGA package. So as you can imagine, this makes also the schematic symbol rather large. This is why I prefer to split it into certain sections, for example, power and decoupling, configuration, various banks, and so forth. FPGAs are pretty power-hungry devices operating at high switching speeds, very short rise and fall times, so you really need to take care regarding your decoupling and your power distribution network. As we said before, we have various different rails. We might have 3.3 volts for a lot of these banks, so VCCO 14, 15, and so on, all the bank voltages. We might have internal core voltages, auxiliary voltage, block RAM voltages, and so on, as well as a lot of ground pins and the transceiver voltages as well. I didn't pick all of these capacitor values out of thin air. There's of course documentation and plenty of it online. For example, the 7 series FPGA user guide by Xilinx, which is UG483. If we scroll down to page 15, we can see the required PCB capacitor quantities per device. And in particular, in my case, the Artix 7 series device, we want the 35T, but we want that in a 484 pin package. And this happens to be the one here. So FTG484 is my essentially package name. XC7A35T is my FPGA of choice. So VCC int, I require one 100 microfarad capacitor, a couple of 4.7, and a couple of 0.47 microfarad. And I go through all of these and simply transfer that into my schematic. We'll get to the placement of these capacitors in just a second, but typically we want these smaller valued capacitors, so 470 nanofarads, right underneath the package, or as close as we can with the smallest loop area to the relevant package pins. Large capacitances such as 4.7 microfarads, or even this very large 100 microfarads, we place somewhere in the vicinity of the package, as we'll see. The various size capacitors cover various different frequency bands. So 470 nanofarads with proper PCB design will aid best at higher frequencies, and even higher frequencies we might be using the PCB planar capacitances between the layers, and for low frequency bulk bypassing decoupling we'll use, for example, this 100 microfarad capacitor. And a similar approach is used across these various power pins. Jumping over to the PCB design again, because of the restraints of this board, I was a bit restricted where I could place my decoupling capacitors. I also had to fan out certain areas of this BGA, but typically a guideline is placing your 100 microfarads, so these large 1206 package capacitors, around the perimeter of the BGA. This could be on the top layer, this could be on the bottom layer, and you'll see I actually have both, so I turn this board around. I have all of my large decoupling capacitors along the perimeter. You could even probably move these capacitors further away as long as they're somewhere in the vicinity. However, the closer we get to this core of the FPGA, or where we have power pins, that's where all of these smaller capacitors appear. If I press 2 to get in 2D view, look at my top layer, let's just see how I did the power fan out. Typically we have a lot of these power pins, so AB14 might be 3.3 volts, AA12 might be ground, we have them sprinkled all around at different voltages. It would be wrong to assume that these are just singular pads, so they have no relation together. What we want to do when decoupling or bypassing an FPGA and doing the fan out is have wide and short traces from relevant pins going to ground and power vias to the internal ground planes. Now I could also place my power and ground lines like so, but that would increase the spacing between these vias and between these traces, and thus increasing my inductance. So what I want to do is place my traces and vias like so to minimize my inductance. On the bottom side, I can then simply place a small capacitor, happens to be a 470 nanofarads, with short wide traces going to these vias. And this is the general strategy I would use. Of course, towards the center of the BGA, where there may be many different voltages, many different power pins, I have to play around quite a bit with how I place my decoupling capacitors. You can see I have a mix of these 470 nanofarads, and these are 0201 capacitors, so very small, and I had to use those because then I can fit them in between the vias and in between these various pads. All in all, I then try to find as many groupings as I can of power and ground vias and place capacitors very similarly, always with these short and close connections. Decoupling and placing vias under the BGA when it comes to fan out is one of the first things I would do generally, because placing vias, especially for a through-hole board like this, will really restrict how you can route your traces. For example, if I hadn't placed any vias and I just routed out my DDR bus, I wouldn't have any space to place down my vias. So it's very important that you route out your vias first when it comes to a through-hole design. Of course, you can use HDI boards with blind and buried vias and micro vias, which gives you more space. But typically to save costs, you would go with a through-hole board such as this. And this is where I strongly suggest place all of your vias first before you do your routing. It's going to be a nightmare otherwise to then reroute, delete tracks, place vias again. Jumping to the next page of the schematic, we have FPGA configuration pins. This includes the JTAG connections, very strapping select pins, so from which devices we boot from, we pull the configuration memory from, for example, these M0, M1, and M2 pins. And I've copied these from a reference manual, the configuration mode pins, and this tells me, okay, for a certain M2 to M0 configuration, I can either use JTAG only, I can use it as a master SPI, connecting to a flash memory, and so forth. You should pretty much always attach a flash memory to your device, unless you're programming it via different means. And so we have this QSPI flash connection, which then hooks up to the FPGA as well. The JTAG header, I've provided some protection in form of ESD protection diodes, series resistors, and recommended pull-up resistors on the TMS and TDI lines. Then moving over to the first few banks. So these are essentially our general purpose pins. Of course, we have certain constraints on various banks. For example, some banks will only be able to run off certain voltages, or have certain speed limitations, and so forth. In general, things to pay attention to are the voltages and speeds they can run at, but also we have various pins that are only capable of certain functions. You might see SRCC or MRCC, and these are clocking capable pins. SR stands for single region, and MR stands for multiple region. Multiple region means any clock input or clock source can be distributed across various regions or multiple regions within the FPGA. This is why my main clock source, which happens to be 100 MHz CMOS oscillator, is fed into an MRCC pin. The oscillator is a simple CMOS oscillator, and I've put a 22 ohm resistor just in series at the output of the CMOS oscillator in case I get any ringing or EMI issues. Other than that, I haven't used many pins of these banks. I've just attached some flash memory, I've attached the clock, and I've attached some PCI Express signals to some of these banks as well as some LEDs. Moving over to banks 34 and 35. 35 happens to be unused or unavailable in this device. And bank 34 is my DDR bank. Going back to the power section, you can see my other banks I've typically tied to 3.3 volts and 3.3 volts over here, but bank 34 I've tied to 1.5 volts. This is because bank 34 needs to interface with DDR3 memory, and DDR3 memory runs nominally at 1.5 volts. Therefore, I wouldn't advise to place any other signals, unless you have signals that need to be interfaced with 1.5 volts, which might be a bit unlikely, in banks 34, for example. You can also see most of the pins of bank 34 are used up for this DDR connection. And this might seem a bit overwhelming at first. How do you even come up with a pinout like this? But I'd like to just finish off the DDR3 memory section first, and then I'll look at Vivado, which is a Xilinx development tool, and this lets us figure out a pinout for DDR memory. I'm using a single memory IC by Micron. This is a DDR3 memory IC, and we have power and signal pins. As usual, we have address, command, and control signals, which I surrounded a blanket with, which essentially lets me give this a net class name, which will really help me with routing and layout later on. We have our various address pins, so A0 to A13, so 14 bits wide, bank address pins, clock enables, and various command and control signals as well. On the right side, we have various data pins. So we have byte line 0, which are bits DQ0 to DQ7, and we have byte lane 1, which is DQ8 to DQ15, as well as the various strobe pins, essentially the data clocks and the data masks as well. Now you can do bit and byte swapping for the byte lanes and the various bits inside the byte lanes, but we've done that on the FPGA side. So we've optimized the layout and routing using the Xilinx tool, which I'll show you in just a second, to do bit and byte lane swapping. And this is pretty much only possible for the data pins. You can also see that I did not provide any termination at all. Data signals are typically internally terminated, but address signals will usually have to be terminated with some termination scheme. If you're just routing out a single device, for example this memory IC close to the FPGA, you can get away with not using termination, and it makes your life a whole lot easier. So that's why I've omitted it in this example. Looking at the decoupling for the DDR3 memory, it's very similar to the FPGA. We have a lot of smaller, lower value capacitors, O201 packages, and we have some larger bulk decoupling, which is placed close to the IC. Now, I'm personally not a fan of laying out and routing DDR3 memory. I don't think it's particularly enjoyable. It's a very wide bus, and this is only for one memory chip. Of course, you can do this for 2, 3, 4, and so forth memory ICs, but even for one, it's not one of my favorite things to do. Again, I've placed my vias first and my decoupling first, so I know where I can and where I can't route my signals later on. My large bulk decoupling capacitors close to the IC. On the bottom side, I have various O201 small decoupling capacitors connected again in the style of the BGA we saw earlier. When routing, we also have to take package delays into account. If I click on my BGA in one of these pins for my FPGA, you can see I have a propagation delay. For example, this pin has about 122 picoseconds. If I click on a different one, this might have 104, and so on. And these package delays are really important to include because we have to length, or rather time match, our address command control signals with each other, as well as each byte lane with each other, or within each other. So if I go to my PCB, I can see I have all my net classes here. If I click address command and control, you can see that within the address command and control group, including package delays, they're routed pretty much almost identically in time. If I go to my byte lane, these are routed around 250 picoseconds, and I've done that using the length tuning tool. So if I go to root, interactive length tuning, this is how I would do that for single-ended signals, or for differential pairs, I'd use this bottom option here. Then I can simply drag and move around and then adjust my fly time, so to speak. I've routed out on 4 layers, and it can get rather cramped. And this is something that you just have to get used to doing, trying routing out DDR memory and make up a habit, floor plan, and so forth. Let's briefly talk about how I got the pinout for DDR3 using Vivado, which is Xilinx free, at least for certain FPGA's IDE or development environment. I create a project, I need to choose my part, then Vivado will create an empty project. Then I can go to create block design in the IP integrator on the left-hand side, just click OK. Then I'll add the MIG or the MIG memory interface generated by Xilinx. So I'll just look for MIG, add that. If I just double click on this IP, I can then start my configuration. I want to create a design, or I can even verify my pin changes and so forth. I'll just keep the default options for now. And I just want to make this design compatible for the FPGA I'm using, but I can make it cross-compatible if I want. I'm using DDR3 SDRAM, and then I can choose a specific memory part or create a controller for a very specific memory part. The part I'm using is M.2 which is quite a mouthful. So I can select M41J128M16XX-125, which is the speed grade. My data width is 16, because I have 16 bits. And I'll just keep the rest as standard for now. We simply just want to generate a pinout. So click next again. Then we can either let Vivado create a pinout, or we can select the pinout ourselves. If I go to fixed pinout, I can then start selecting which bank I want, for example, bank 34, and selecting a certain pin. Now, this could be based on maybe your HDL designer's preference of how they want things grouped within the FPGA, or it could be from a PCB design perspective. What is easiest to route out? If I put DQ0 on T1, is that easier than putting it on U1? However, there will be certain constraints in doing this. Therefore, it might be easier just to start with new design and then alter Vivado's suggested pinout. Lastly, let's look at quite a cool aspect of this FPGA, which is that it includes PCI Express high-speed transceivers. Up to even 4 lanes receive and 4 lanes transmit, so it's PCI X4. This runs off nominally 1.2 volts, which is rather an odd voltage, so we need a specific rail for this transceiver section. We need a calibration resistor R700, which is 100 ohms. Then we have RTX, which all require AC coupling capacitors. And on the other side, we have our clock, as well as our RX lines. So there isn't much to that. And these get pretty much routed directly to the M.2 connector. PCI RX, 4 lanes, and PCI TX, 4 lanes. All differential, of course, a reference clock, and various control signals for PCI Express. For example, the wait signals or I2C configurations, and so forth. The M.2 connector simply has then power and ground pins, and I've had a lot of unconnected pins because I'm pretty much just using the PCI Express functionality. I got this M.2 card footprint from Timonsku's GitHub account, so just by Googling, and these were for Eagle and KiCad, which I had to then import and convert using Altium's KiCad importer, so that was fairly straightforward. It is a bit hard to find M.2 specific pinouts or footprints or general dimensionings of M.2 connectors, also pin spacing and so on, so this was really useful that this was available. Overall, this is simply about 22 millimeters wide by 80 millimeters long, and again fits into any M.2 key B slot. Then I have all my PCI Express connections at the bottom. I have my JTAG using a tag connect header, and that's about it. We're looking at the PCI Express routing. I have various differential pairs going to my card edge connector, and right at the card edge connector, I've placed fairly symmetrically these AC coupling capacitors for the TX lines. Then, as soon as I change layers, I also place these transfer vias, which are essentially grounded vias, to maintain a proper return path. When I'm switching, for example, from layer 1, my reference is directly below layer 2. But if I'm then routing on, for example, layer 3, my reference will also change to layer 4. And then that's because I'm routing as a strip line now. So that's why I have these transfer vias close to make sure I have proper field coupling and still maintain a proper return path even in the Z direction. Strictly speaking, PCI Express signals don't really require length matching between the pairs. However, I've matched them between the TX and between the RX lines. And of course, I've provided intra-pair differential pair matching, and this needs to be pretty tight. So for example, looking at the PCI RX group, I've routed them within about a picosecond difference within the pairs. Because we're operating at rather high bandwidths, rather short rise and fall times. I've tried to route as much strip line as possible because these are high speed signals and I get some good shielding effects for my ground planes either side. I try to minimize the number of vias, of course, I use. Of course, with through-hole vias, you are going to get stubs. I know this was a rather brief overview of this project, but I hope it gave you a bit of an insight as to what parts are in this system, small things to pay attention to when routing, laying out, and so forth. Lastly, I'd like to just show you also the documentation and the files I produced for PCBWay to get this board then manufactured. One really cool feature in Altium Designer is the Draftsman capability. I can add a Draftsman document, and this is essentially documentation for assembly, for example. If I open my Draftsman document, I can add various views, for example, these realistic views of top and bottom. I can add name, logos, and so on. I can show images of my layers, so layers 1 to layer 8, and these can be updated in real time if I right-click and then import changes. So anytime I make a change to the PCB, this whole document can be updated instantaneously as well. I can add isometric views, and most importantly, I can also add assembly views. Because I had the bottom and top layers assembled, this is taken directly from the PCB. I can change, for example, bounding boxes, I can add silkscreen, change my reference designators, and so on. And this is really helpful for assembly as well. This I can then export as a PDF, as well as my bill of materials, my component placement file, which is my pick and place or footprint position file. And then I also provided PCBWay my Gerber files packed into an archive, including manufacturing information. As a text file, say I need a certain thickness, I want an edge connector and please see attached files, castellated hole, please see attached files for locations, how many layers I want, what materials I want, minimum spacings, and then also my impedance control requirements. So I want a single-ended line on certain layers with given references, and I want a nominal trace width to be about 0.08 millimeters because I have fairly tight routing. For PCI Express, I also require 85 ohms controlled impedance, and for my DDR differential pairs, I went with about 100 ohms differential impedance. I already pre-computed a stack-up for this, so this is my suggested stack-up to PCBWay, and there were some minor adjustments made, but it's nice to get into a certain ballpark or to give your manufacturer an idea of what you need. Of course, it's always really important to talk to your manufacturer to see even what's possible, or what can be more easily produced. I showed images of where I need the castellated hole to be, and for example where the edge connector is, and so forth, just to make sure there's no confusion and we can avoid any unnecessary mistakes. And as you see, the result is exactly what I wanted: castellated hole, edge connector, parts placed perfectly, and so forth. Thank you very much for watching this video. I hope it is helpful and gave you some small insights into what it's like or what you need to do to design an FPGA-based board with some high-speed interfaces. If you haven't already, please make sure to like the video, comment, and subscribe. Thanks again for watching, and I hope to see you in the next video. Bye-bye.